So first up is Bernice Zee. Bernice is a senior member of technical staff at AMD Singapore. Here, she's advancing new package development by driving next generation failure analysis techniques. She has her Master's of Science from Singapore's NTU, Master's of Material Science from Singapore's NTU, and she's been previously contributing to both IPFA and ITSFA conferences. Today, she's going to be presenting on some of the newest failure analysis challenges that heterogeneous integration has created, and we'll dive into some specific case studies that show some pretty interesting points. So with that, I'll hand it over to you, Bernice.
Thanks, Mike, for the kind introduction. Good morning, everyone. It's my privilege today to actually kickstart the second day of the Known Good Die workshop. For those who listened in yesterday, I think this presentation is a good fit in from where we left off. So yesterday, I think for those who attended, David from NVIDIA talked about how Moore's law was slowing down and how stacking and advanced packaging were going to take up the slack in terms of keeping up with the compute demand. And after that, I think Zoe and Yuri gave a good talk about, how to alleviate the problems associated with known good die through diagnosis and testing. And, typically after diagnosis and testing, you would want to find out, if a die really went from good to bad, why did it fail? And the best way to do it is actually through failure analysis. But failure analysis is not so straightforward now with the new advanced packaging. And today I'll share about some of the challenges we face while doing advanced packaging failure analysis. So here's a brief outline of the presentation today. First, of course, we cannot do without introducing some heterogeneous integration, how heterogeneous integration is driving next generation packaging technologies. And after that, we'll talk about the importance of failure analysis and how it helps to let us attain good quality known good die, as well as implement new packaging technologies. And with that, right, because we expect failures when we develop new packaging technologies, what sort of requirements in terms of failure analysis do we need, and how we should progress in developing the new capabilities in order to continue to find failures to improve die yield and quality. And then to wrap up, we'll talk about some case studies and then conclude this presentation. So, everybody's not new to heterogeneous integration. As we know, as the semiconductor industry progresses on and Moore's law starts to slow, in order to continue to, keep up with the pace of the compute demand, we need to think about new ways to continue to keep up with the pace when Moore's law can no longer scale at the rate it used to scale. So as you can see over here, right, in this interconnect and roadmap over here, you can see that there's actually two types of packaging styles that we are seeing right now. One is in terms of stacking. Over here, you can see there are more and more dies that are put on top of one another. And at the same time, there's another trend that we're noticing where people are splitting up dies and combining them in reconstituted wafers or in reconstituted interconnects such as TSVs and redistribution layers. So these become important because we want to continue to miniaturize, reduce latencies in communication between dies, and as well as continue to have high bandwidth. But this is becoming increasingly more difficult. And because of because of these, right, we need to start to think about new ways of packaging, and stacking is a very good option because firstly, it allows you to maintain a very small footprint, but increase functionality of a die. And this integration, right, it allows you to, instead of having one very large monolithic die, we could split up the die into smaller ones, which improve yield. And at the same time, because you can optimize the functionality and the performance of a small die much faster, you mean that you could actually reuse IP very easily and then pick and place what kind of functions you want in a particular package by picking and placing. But of course, these bring about their own challenges. For example, in stacking, in TSVs, you expect a lot of reliability issues because they are very tall and very thin and very prone to cracking because of the very ultra high low K materials that are used to make them. And at the same time, right, when there are defects in these TSVs, how would you actually want to be able to visualize the defect when they're so small and you need to decide in which layer the defects are actually going to appear? And in the disintegration, right, when you have many chiplets that need to be combined into a single package, you need to think about, oh, how am I going to ensure that the speed of communication between these dies are going to be good and fast, like if they were on the same monolithic die? And how would you prevent crosstalk interference when when there's so many dense interconnects on a particular substrate? So that's when heterogeneous integration comes in, and the vendors have to start thinking of more novel ways of trying to address all these problems while giving us the benefit of the increased performance and speed. So over here, here are just a few examples of some of the next generation packaging technologies which have become publicly available. So the different players doing different things. So for one, we have the organic substrate vendors who are also trying to innovate to provide high density organic substrates as low cost alternatives to silicon interposers, which generally tend to be very expensive. And they actually try to achieve high density fine pitch interconnects by actually creating very thin interconnects at the substrate layer through copper RDLs, which can be in the line width of 2 microns, and they can hold pad pitches of 40 microns. So this is a substrate vendor's solution to an interposer substitute. And then over here we have the TSMC wafer-on-wafer stacking, which I think everybody's very excited about, because this will be the first true real 3D package that we'll be seeing on very advanced semiconductor products in the future. And for these, right, because they're very high fine pitch kind of interconnects, I guess the assignment comes when you can actually stack maybe, for example, logic with different types of memory on top, or maybe in the future, beyond memory, you could have other functionalities being built on top of this particular single die here. So that promises more power efficiency and lower latency in terms of communication between the dies. And last but not least, we also have things to help to improve chiplet communications. So I think the most famous example would be the EMIB technology that was developed by Intel a few years back. And they have really productized it with their the products with the GPU as well as the APU onto a single substrate. So these chiplets actually are supposed to be better performing than interposers, just because the interconnects are a lot shorter, and it provides a good communication path between the different chiplets. So where does FA fall into this picture of all these new packaging technologies that are being developed? So a very key thing, if you see in this diagram here, right, whether you're talking about designing new dies, new packages, whether you talk about manufacturing using new advanced packaging technologies, whether you're testing them, and then when you sell it to a customer, right, as there is testing you and debug, you realize that as parts start to fail, right, customers will start to ask you, why is my part failing? If you're on the development team, you'll be asking, oh, I thought, I've got the processes all right, I selected the right materials, I followed the, the process conditions for assembly. Why is it still failing? So that's where failure analysis comes in, to actually tie in all these different functionalities together to help to solve and root cause why a package could fail. And this is actually very key in terms to the product time to market cycle, because as you can see, it's needed in every stage of the development. And at the same time, it's also essential for achieving the highest possible quality to make any known good die. Because if you think about it, if you design a good die, but after assembly, because you put it onto a substrate and there is some chip package interaction and it fails, you would like to know why that happened. And then from there, you could further fine tune probably the process, either in the assembly line, or you could improve the die design to make it more robust. And so it's like a feedback loop, which is continuously continuously moving on and round so that we can continue to improve yield and achieve better products. So in next generation packaging technologies, what exactly can go wrong, right? So if you take each of these die to be actually known good dies that you obtain from a supplier and you have put it onto an interposer, and then on the interposers put on the organic package, actually it's actually no different from a flip chip package in the end, right? And the failures that you will observe are probably similar in type. Like for example, you could get microbump delaminations, microbump cracks, misalignments, warpage that will cause non-contact bumps. In organic packages, you still get the same old copper trace damage if there is something wrong at the substrate vendor side. And in the interposers, because of TSVs and you can get delaminations, electromigrations and cracks. So if we want to find defects, we need the right techniques to go and find each of these failures that we'll probably observe, which will cause shorts, open or resistance and leakage. So before I proceed any further, perhaps Mike, if there are any questions, I could take them now before I proceed on to hardcore failure analysis techniques.
Yeah, Bernice. So when you look at all of these different types of failure mechanisms, in your experience building or doing failure analysis on AMD products, which one, if you were to rank these in order of amount of times you've seen something or quantity of problems, would you say, and I'm specifically speaking to our advanced package technologies because I know C4 is all over the place, but in the advanced process technologies, are you seeing more problems with warpage from huge MCM packages? Are you seeing in specific microbump damage? Where's most of the time being spent these days? So
thanks, Mike, for the question. So I think the number one issue now is, I think we've realized that as we want to integrate more chiplets, right, our packages are getting very big. And warpage is definitely one of the key issues that we face. And with warpage, right, you will end up getting delaminations as a result because there's a high stress at the edges. And then when you put these parts under reliability testing, you will end up inducing a lot of stress, and the corners, because they have the higher stress, will start to delaminate first. But at the same time, because now we are having 7 nanometer products, and you're going to the ultra low K type of materials, right? ILD delam, which is in the die, is also becoming more and more commonplace. And if you think about it, right, when you stack up things, you have to figure exactly where's the delamination you're going to observe. Is it going to be here? It can happen at any of these interfaces, and then you need to be able to pinpoint exactly which of these interfaces is failing, and then root cause with and discuss with the the product owners as well as the foundries how to improve that.
Okay, thank you.
Okay, if there's no further questions, maybe I will proceed on. So we're just talking about the types of defects that we are expecting to see in the advanced packaging technologies. And so now we'll just talk about what exactly are the requirements needed for next generation package FA in order to find the defects that we just discussed about. So first and foremost, right, because we generally want to not tear our the product down so that we can continue to do further testing to isolate the failure. I think usually the first step that we'll do is actually non-destructive testing, which will involve both electrical testing as well as imaging. So in terms of the non-destructive electrical testing, right, which is the fault isolation part, on top of the diagnostic test that you'll do first, on the ATE, we too also need to do some form of electrical fault isolation to get the exact coordinate on where to focus on. So in order to do that, right, we need high spatial resolution in the X, Y, and Z direction. So the Z direction becomes very important when we talk about die stacking. And because everybody's heading towards low power, because as you put more and more functionalities together, you don't want your part to overheat. The low power aspect of the packaging actually becomes very challenging because it becomes much harder to detect failures when they are very low electrically powered. So improved electrical sensitivity is always important for us to keep pace in detect our defects. The next part is the visualization. So as things become smaller, the standard ways of imaging become much harder because, you know, it's very hard to see a 40 micron microbump as opposed to a 80 micron C4 bump. And the TSVs are even smaller because they're really thin. So we, again, you know, resolution is always important when we want to do FA. But at the same time, we also don't want to be taking like a very long time to image things, right? So acquisition speed becomes very key. And then after that, once we have really isolated a particular location, right, we want to be able to do physical failure analysis, meaning we want to start tearing down the part and, you know, seeing the defect and then analyzing it through scanning electron microscopy or you know, energy dispersive X-ray to find out foreign materials, right? We need to do sample prep. And we are looking now at high precision because things are much smaller. We want high throughput because we don't want to be waiting days to do a cross section or to do analysis. And at the same time, because sometimes defects could be very small, we need improved analytical sensitivity in order to do that. But on top of all that, right, we always has to be a balance between time to results, you know, physical resolution limits of techniques, as well as the cost of ownership. So as we do failure analysis, we always need to consider all these in tandem with the products we want to analyze.
So Bernice, when you're trying to localize where a failure is, how does test engineering support you? Do they have to write special code to light up the location, or has some product engineer said, I think it's here, or do you just get this thing and somebody says it doesn't work?
Okay, so typically you go through ATE testing, and through the test program, we could actually get a binning of the type of failure that the product is failing. So for example, it could be a power supply fail, right? Power supply short. And then once we know it's a short, we will apply specific techniques to you know, localize a specific area to focus on. Or with a functional test, then there are other failure analysis techniques which are die level related, where they could run the tester and then have a detector to detect like emission sites. So it's a variety of, I mean, it works. And it starts from the ATE tester and the test program that is written by the designers. And from there, we can, as long as we can determine which pin to test on our failure analysis tools, we should be able generally to get a specific spot to focus on.
Thank you.
So now I'm just going to briefly talk about some of the key techniques that we use to do failure analysis. So one of the more commonly used ones is lock-in thermography, and it works on the basis of when you have a short failure, there's generally a lot of heat being generated at that particular short position. Like for example, if it's at the microbump, there's a short, there's a lot of heat generated here. And this tool actually helps to detect shorts through thermal emissions. And the other aspect of it is that's we can attain Z-axis information through the phase data. So the phase data actually based on thermal diffusivity properties of a material. So for example, polymers tend to be less conductive and have poor thermal diffusivity. So it takes a longer time for the heat to come out. Or if the defect is very deep settled in the package, right? It also takes a longer time for the heat signal to go through and reach the camera sensor over here. So we could actually come out with test chips which at different interfaces have a particular like a short, so that we can create a curve which will identify, oh, so this is the die level because the heat comes out the fastest because it's over here, and to the camera it's really near. And then after that, there's the microbump shot, which is over here, which is again quite near the camera, but it's slightly further from the die. And then the C4 bump shot, which is the furthest away from the camera and takes the longest time for the heat to actually diffuse up. So this model actually helps us to create a sort of like a template where if we test a sample with an unknown failure, right, and we can plot out this graph, we will be able to determine exactly at which interface the short is occurring at. So the thing is, in order to develop this, right, it actually takes up a lot of time to create the model. And at the same time, if you have a very deep-seated defect, right, it takes a longer time. If it takes too long a time for the heat to come up, sometimes if you continuously test the sample, right, the defect could actually get aggravated and you might end up blowing up the whole part, which is something that we don't want because that means we lose the cost of failure. So I think the challenge for this technique is actually how to improve the accuracy and the time of results using this tool. So by working with the vendors, right, they actually come up with new algorithms which help us to actually do curve fitting to reduce the time to actually detect get the phase information, and from there, right, it can automatically stop measurements and prevent us from running the test excessively long. And at the same time, right, because of the curve fitting which the software can do, it can get us the exact phase shift value we need in order to get the most accurate results. So this is some of the developments that the vendors, when we feedback to them, like the difficulties we have, these are some of the things that they came up with to help to improve failure analysis, accuracy, as well as time. Another technique that we often use, especially for opens, is the EOTPR technique, which is the electro-optical terahertz of reflectometry. So if any of you are familiar with the time domain reflectometry, it's actually pretty much similar to that technique. It's just that in order to get higher resolution for like a very fine interconnects, right, you need a faster rise time. And in order to get a faster rise time, you need a higher frequency signal to be pumped into the device under test. And so what EOTPR actually offers is a terahertz signal, which is much faster than a gigahertz. So over here, you can see, right, we have a waveforms that are obtained from different references. So similar to a TDR, we need a good substrate, a bare substrate, the field unit, as well as a substrate for interposer if you're talking about 2.5D, so that you could get reference curve and decide exactly for the failure unit which waveform is following and make a decision on where the open is. So as packaging technologies become more complex, right, sometimes getting the references we need to obtain these reference waveforms becomes increasingly more difficult because it's very hard to tell a vendor to create, for example, if you have multiple chips, different missing, they ask them to create different variants of chips which have so-called the reference that you need, right? So it becomes very difficult for them to make it because all you need is just one, and they're not going to change their processes just to create that reference for you. And if you are needing to create that reference on your own, right, sometimes it's very challenging because it's difficult to do it uniformly. So in this case, right, what the vendor did is they actually developed a modeling circuit software where you could actually generate a waveform of your reference based on the known circuitry and the design that you have in your package. So that allows you to create different waveforms and introduce defects in different areas so that you could compare it to the waveform that you got from your field unit. And then from there, make a decision where exactly is the open location being observed. Another technique that has been around for a while, but is gaining possibly more notice, is the magnetic field imaging. So in this case, this is different from the thermal because instead of measuring heat, right, it's actually extracting a current density path based on the magnetic field that a current might emit during the testing, right? And so based on that, it's good for stacked dies because it actually, if your defect is very deep setted in your package, you could still get a signal as to in the XY direction where exactly it is without having to wait for the heat to actually be transmitted out. And now the vendor has actually developed software to help with the Z depth localization as well, as it starts to extract and extrapolate the current path. And based on some calculations, it calculates exactly in the Z depth where is the defect. So the 3D path solver method is still quite new, and I think in its current state, mainly experienced users will be able to, decide based on this image where exactly is the defect. But from the last discussion we had with the vendor, I think they've made this a lot simpler for a general user to use. And the space domain reflectometry is actually, yes.
Bernice, just trying to get some of the questions answered. In your first set of FA tools, you were talking about the acoustic X-ray. What specific types of defects were you looking for there? Were those specific power shorts, or were they just thermal in general, or what specifically were we looking for in that thermal emission? What type of defects?
We're looking for short defects or leakage.
Short defects for leakage.
Yeah, so those are the types that will generate heat.
Okay, so anything that'll generate heat, and then opens was for your optical.
Yes.
And then the other one, the last one, is for potentially still heat, but lower power heat, and potentially more specific to current draw as opposed to actually looking for the heat.
Yeah, so this one is based on the current density. So if you have a short, you will generally draw more current in that area. So it will turn up in the current density map as a bright spot. Yeah.
Got it. Okay, sorry, continue. Thank you.
So the other part of the magnetic imaging is actually the space domain reflectometry, and this is also used for opens. So this magnetic imaging technology, magnetic field imaging, also has the option to do opens, but it does it differently from the EOTPR, which I was talking about. So in fact, it uses a RF signal instead, and if there is open, right, you will actually see that there'll be a location where the signal gets totally reflected, and it actually appears very bright. So the RF power cannot be transmitted beyond the spot which is open, which is I'm being blocked by this, but it's probably just over here. Okay, so I'm just going to move on to the visualization techniques which are being used now for advanced packaging. So the most common technique that we use and have been using for a long time is acoustic imaging. So it actually uses ultrasound, and depending on the frequency, the higher the frequency, the better the resolution you get. You could image different types of interconnects. And you can see over here, based on the focal length, you could decide where, which interface to focus at. So what is needed for optimizing acoustic imaging for the advanced packaging technologies is you actually need high-speed data processing, because you can see, right, now these bumps are much smaller. There's a lot more data collection, and you need to select specific times in space to gate in order to image this. So you are going to need a better data processing in order to get finer differentiation of the signals to gate. And at the same time, you also need a constant time so TOF stands for time of flight. So as I mentioned earlier about the warpage, right? As packages become larger, you expect a lot more warpage. So if your time of flight, meaning the focus of the Z doesn't stay constant, right? You will end up getting blurred images because the focus is no longer maintained at a specific time of flight. So that needs to be corrected with active Z movement to maintain the focus of the acoustic microscope. Something that is probably familiar to everyone is the 3D X-ray microscope. It's similar to the medical type, where you do tomography by collecting many slices of images of the object, and then you can reconstruct it. And you can see over here, you could see microbump cracks, you could see substrate anomalies, substrate cracks. And these are very easy to see because it's literally what you see like when you get an X-ray by yourself in the hospital. And I think the challenge to these is as defects get smaller, right? How, you know, there is always the resolution limitation, which is limited by the physics of X-ray. And at the same time, you know, the time to acquire this image will actually take like 8 hours just to acquire. How would you want to speed this up, especially if you're wanting to do 3D X-ray in the assembly line? So I think these are some of the challenges that we face in terms of, you know, these non-destructive testing and non-destructive visualization techniques in FA. So I'm going to just cover a couple of case studies where we use a combination of all the techniques we talked about to root cause the failure of 2.5D devices. So over here, we actually
Bernice,
have
not to derail anything, but when you go through these case studies,
yes.
It would be good if you could also, I think there's two or three different case studies. About how much time did you spend in each of these trying to get to the actual fault isolation? It can be, you know, weeks, months, days, hours, you know, just to give the audience kind of a general gauge or a magnitude of how long these types of things do take, because I know they're pretty labor intensive.
So I think it depends on the information that's available to us. Of course, the more information that we have in terms of what test did fail is very important. If we have the design info of the package, that will also help us greatly. And if one of the non-destructive testing techniques actually give us a very clear signal at the start, right? Usually, I think we could finish a failure analysis within a week or two, generally. So of course, those which take longer are those which are a bit more complex and the signatures are not as clear-cut as we would like them to be. And also, if the package is very new and we don't have much information about it, then that also takes a much longer time because we need to gather feedback from a lot of people, be it the designers, foundries, yeah.
Yeah, and then once you actually have to go to destructive FA techniques, you're adding weeks and weeks to the actual process, correct?
Yes, depending on what exactly needs to be done. If there's a lot of deprocessing, yes, it will take weeks because we need to go layer by layer to inspect. So that's the case when we don't have a good sense of where in the depth, the Z depth of the package, where exactly is the defect. So we need to go slow because we need to inspect every single layer. So that's why when I was talking earlier about the spatial resolution, we're talking about XY, which is in 2 dimensions, and now in Z because we are going to go into 3D in, I guess, a few years or so, right? Because there's a lot of talk and there are a lot of people developing those types of packages already. So those would take much longer.
Okay, thank you.
Okay, so let me quickly go through the case studies in view of the time. So in this case, right, the first step that we took for this short failure was we decided to do acoustic imaging because we wanted to see whether there was any gross defects. But as you can see in this image, right, at the we couldn't really see anything in the micro bumps as well as the C4 bumps. But when we went on to do the thermal emission, right, we could see that there was actually an additional site in the reject unit over here. And using the model method where we wanted to isolate the defect in the entire Z depth of the package, we actually found that it was near the die interface, which is the pink dots represent the experimental data, and the solid lines actually represent the model that we created based on known defect location units. So based on the phase shift measurement, we found that the defect was actually located probably in the die metal active because it's very close to the die line. And then we went on to do TIVA, which is a laser-based for isolation. And we actually saw there were actually TIVA sites over here. And then when we did the PFA results, it was root cause to metal tree damage, which you can see very clearly over here. So as mentioned by Mike, when you asked the question earlier, something like this will take probably 20 days. that's the fastest case. But of course, it could take much longer, especially when you need to do TEM and you need to do TEM sample prep. So this one didn't require TEM sample prep. So it's just manual delayering and being able to see a very gross defect. In the second case study, right, we were luckier this time. We could actually see something in the acoustic microscopy. You could see over here, there's some form of delamination at the C4 bump interface. And in the lock-in thermography, right, it confirmed again the CSAM results about it being near the substrate. As you can see over here, the pink triangles now line up very close to the package, the C4 bump interface. And then in order to ascertain that, you know, that hypothesis, right, we actually went to go down to do a localized die thinning. So when we do this, right, localized die thinning is actually very tough because we need to ensure that we don't induce any damage to the die. And at the same time, we want to get it as thin as possible so that we can get a more focused thermal emission site. So if you compare it to you know, the previous one, which it looked very dispersive, it's still kind of debatable exactly how big a defect we're expecting. But after the deprocessing, you realize it's actually a shot between two C4 bumps. It's really small. And when we did the 3D X-ray, right, we could actually see it. Over here, you can see there's a ground pin, C4 bump over here, and the signal pin. And there is a trace of a delamination with some sort of material that is connecting these two pins. And when we did the FIP cross-section, we could actually see that there was actually a solder flow at the passivation and underfill interface, which caused the short. And the last case study will be about talking about open failure, right? Where we tried very hard to do it non-destructively by looking at it acoustically, but we couldn't really see any anomalies in both acoustic imaging and X-ray. So we turned to the EOTPR method to help us find exactly where the open was, and it actually identified it to be somewhere between the substrate and the interposer. And in the 3D X-ray, while it may not be superbly convincing, we did see signs of cracking here, and then we confirmed it using cross-section over here. So you can see the cracks. And okay, we still have one more, really quick one. So there are cases where we can't see anything in thermal emissions because the short is really big. And as a result, right, luckily in CSAM, we were able to see a CSAM anomaly. And when we did the PFA, we found there was actually some foreign material that was causing a short in the microbumps. So, you know, there's no one technique that will help us to root cause a failure. Sometimes it requires, you know, sometimes we are lucky, only one technique is needed. Sometimes we're not so lucky. We need like multiple techniques in order to confirm the failure. Okay, I think this should be the last one. I didn't realize there were so many case studies. Okay, so for this case, right, the thermal camera over here, we could see a site. In the CSAM, we see CSAM anomaly as well. And when we do FIP cross-section, we can actually see metal-metal shorts. So in this case, right, this sort of failure analysis is probably the best type because there is a lot of assurance that we are in the right direction. And these will be much faster. So in summary, you know, failure analysis as packaging technologies get more complicated, right? It continues to be very challenging. And, you know, in many cases of, you know, product design, right, for some strange reason, right, because even though things always fail, no one really, you know, considers or thinks about how to do failure analysis when they design a chip. And when it fails, right, it lands up like, oh, what are we supposed to do? And we land up having to work through, you know, many iterations. We might have a few causes not found before we finally find out what's the best way of doing it. So, you know, despite failure analysis being very important to achieve, you know, no good die quality, right? The design aspect doesn't really consider, you know, how to make life easier for us when they design a chip. It's just all about performance and, you know, reduce latencies and high bandwidth. But of course, I guess failure analysis is just part of the ride, right? And we learn a lot from it. So, you know, as things change, we always need to innovate failure analysis techniques so that we keep up with, you know, the packaging technology advances. And with that, I'd like to thank everybody for their time, as well as the people who contributed to this presentation. Thank you very much.
Okay, Bernice, we have a couple of minutes for a couple questions. I would like to say thank you for telling me that I don't provide you guys any design consideration for failure analysis, but it's okay. Publicly shaming me is a good way to get some feedback.
No. I think,
no,
I mean,
I'm just kidding.
Yeah. Just saying, I mean, we will be working closely together, right? So that's always
definitely,
good.
yeah.
Yeah.
For everybody, while we go through these questions, a survey should have popped up on your screen. If you guys could fill that out, that would be great. That'll help us for future things. So it looks like there's two unanswered questions at the moment. The first one is, what specific techniques have we developed, or if you can talk about them, have we developed to kind of prevent any cross-section induced, the actual physical cross-section induced damage while we are actually doing our cross-sectioning, so that we're not adding stress damage to the product?
So I think right now, right, the most common method that we use is FIB cross-section. But, you know, FIB cross-section, because it's a gallium beam, right, it takes up a lot of time. So in recent years, there have been the plasma FIB. So I'm not sure if people are familiar with the gallium FIB. So it actually uses gallium ions and bombards the material and removes it. But then in plasma, the plasma FIB, it actually uses a bigger kind of ion, which is the xenon ion. It's like throwing a ping pong ball at something and chipping away, and throwing maybe like a basketball at the same material and chipping away. So of course, if you throw something bigger, it's going to mill away faster. But even now, we're finding that, you know, if you're going to cut, doing like, for example, like a wafer to wafer stack kind of PFA, like a physical failure analysis, like for example, a HBM, you could potentially still take a very long time if you want to cut through the entire stack. So I think what's happening now is out there are actually people starting to use lasers to do the cross section. So the laser, of course, you're not talking about those green lasers or those super high power lasers. You're talking about pulse lasers where you only expose the material to very short bursts of the laser, and you actually don't really induce a lot of heat damage onto the part. So that's something that in the horizon, which you know, people are looking at to improve the speed of a cross section without having the effects of like a mechanically induced artifacts on your cross section.
Excellent. Okay. Thank you. There are more questions. Unfortunately, I think we have to kind of move on so that we can get everybody kind of out of here on schedule. So thank you very much, Bernice. There's lots of outstanding questions. If you've asked a question, feel free to email Bernice or Ira or me and see if we can't get you guys in contact to get your questions answered. The discussion should always continue after these types of talks.
So thank our sponsors once again. Our diamond sponsor, ASC, providing design, assembly, tests, materials, and components, logistics services to the electronics ecosystem through their different entities. So thank you, ASC. Thank you, Advantest, global leader in ATE, doing the heavy lifting of the testing to make all these advanced technologies available and reliable. To GelPack for solutions that allow material handling, both in fab and transport of very valuable devices. So thank you also to GelPack. And lastly, thank you to Mulbauer Group in terms of factory automation and material handling. So thank you for sponsoring this event and making it possible. I want to remind everybody that the final session is tomorrow morning, Friday, September 18th, from 8 to about 10:30 a.m. Pacific time. We'll talk about solutions in particular. Your Zoom link that you used today is good for tomorrow. You'll also get a reminder. And with that, but I thank everybody for joining us today, and I wish you a good rest of your day and look forward to having you join us tomorrow. Thank you.